So, our first speaker today is Andy Fabian, who is a long-standing fellow here and former master. Andy is former vice master here until 2 years ago, until our last speaker today, Martin Jones, became vice master. So we kind of got bookended vice masters with the day today. Andy is the Royal Society Research Professor at the Institute of Astronomy. He's been President of the Royal Astronomical Society and has many honours, an OBE, he's a Fellow of the Royal Society. He's been awarded the American Astronomical Society's Daniel Heinemann Prize for Astrophysics and the Gold Medal of the Royal Astronomical Society. He also has a prodigious number of papers and an H-index that, for those of you who are in the world of worrying, being interested in things like that, that is, astronomical. Today, Andy is going to talk, as you can see, about astrophysical black holes. Andy.
Thank you, Mary. Yes, I think you should all be pleased that the lunch has not been designed around my talk. Anyway, I'm going to talk about astrophysical black holes, and that's because I'm an astronomer, or as Americans would call me, an astrophysicist. And black holes are now part of astronomy. We know there are lots of them out there, and they play a very important role. And that's what I want to try and communicate with you today. I want to take you back to start off with 50 years to the start of black holes being part of astronomy. Back in 1963, according to Wikipedia, Trinity, St. John's, and Gonville and Caius decided to form a graduate college, which of course turned into Darwin College. But also for astronomers, very important things happened. Quasars were discovered, the Kerr black hole solution was discovered, and relativistic astrophysics began. And I want to talk about these two things which are completely connected and take you through the 50 years since then very quickly. Here is a black hole. This is the first quasar that was discovered. It's known as 3C273, which means it's in the third Cambridge catalogue of radio sources. It's number 273. This is a Hubble Space Telescope image of it. This structure here is part of the system, and it is a jet that sticks out of this thing. And this cross is produced by the support structure in the Hubble Space Telescope. But the fact you can see that cross, and you can see a cross on that object there, indicates that they're point sources, completely unresolved by the telescope. This is a star in our own galaxy. This is clearly brighter than this, but this is 1 million times further away. Then, because of 1 over r squared law, inverse square law for radiation, take things further away, they get fainter, it goes as a square, so this is 1 million times brighter. This is 1 million times the luminosity or power of the sun. That's truly enormous power, okay? And this thing was identified by radio astronomers and then optically by Martin Schmidt at Caltech, realized that it was at this phenomenal distance. Back in the 60s, there was squabbling about, is it really at this distance? What is going on? But one of the things that was realized pretty early on in this object was it varies. It varies in brightness by factors of 2 in a week. Okay? This means the size of the system, the size of this light source, can't be bigger than a light week across. Otherwise, it would the variations would all get mangled up. So that means it's compact. Now, the sun is 8 light minutes away. In astronomy, we talk about distance often in terms of how far light can travel in a certain time. So the sun is 8 light minutes away. This thing varies in a light day. That means it's roughly the size of our solar system. The size of our solar system, but a power which is 1 trillion times the power of the sun. This is something very, very unusual, and it was not long before some astronomers and physicists started to associate it with black holes. Now, the idea of black holes is actually fairly old. It's over 200 years old. The relativistic black holes we know about are due to three people. That's Einstein, that's my next slide, and then this man, Carl Schwarzschild, and this man, Roy Kerr. He's a New Zealander who got his PhD in Cambridge, and I took this at his 70th birthday celebration in New Zealand. He died in 1915, the year that he discovered this solution. It was on the Eastern Front during World War I, of course. The whole idea of black holes is over 200 years. Another Cambridge person, John Mitchell, of course, back in 1784, people like this trained for the church, so he actually was a vicar, I guess. But in those days, they spent a lot of time thinking about natural philosophy, or at least many of them did. And he knew, and I put all this in terms of modern units, but he knew about the sun and Newton's laws about gravity, and he knew that to escape the sun's gravity, you would have to throw something off at 600 kilometers per second. He also knew back then that light had a velocity. This was known in the 17th century by observations of the moons of Jupiter. The velocity of light is 300,000 kilometers per second. The escape velocity of the Earth is 11 kilometers per second. The sun, it's 600. He reckoned that if what you did was you stacked 100 million suns together, okay, stack them all together. Let's not talk about how you do that, but let's just imagine a thought experiment. Then the escape velocity of that object would then exceed the velocity of light. So John Mitchell said, it is therefore impossible for that object to be seen. And that was a very simple argument. It's actually a good argument. In terms of what we know now, it happens to give the right answer for the wrong reason. But never mind, the concept that there could be objects in the universe which we can't see, yet would be very massive. And he even mused that how you might detect it is if it was near another star, an ordinary light in a bright star, you might see that star moving according to the gravity of this object. These objects are called black holes. The concept of the black hole, the word black hole, was coined by John Archibald Wheeler in 1967. So what they called it then, I'm not going to go and discuss. This man was very important in all of this in terms of coming up with modern black hole theory, and this is Albert Einstein. Here is a letter he wrote from Zurich in the 12th of the 10th, and that's 1913. And what we can see there is a diagram. That's the sun, and he's got a light ray going past the sun, and the light ray is being bent by the sun. So he was starting to think about how light can be bent by gravity. It's actually the wrong answer. The number he's got there is actually a factor of 2 wrong, but never mind. He got it right a few years later. And this is the concept of curved space-time. And that is what underlies black holes. Some of us draw diagrams like this about black holes. This indicates space, and this is the black hole, is actually where it's all gone down like this. So basically, space and time get changed enormously by this enormous mass, which is within a small radius. Here's an analogy. This is the Victoria Falls, okay? And you notice that if you were in a boat somewhere here, eventually you get to a point where no matter how hard you row, you go over the edge. And similarly, with a black hole, there is an effect whereby if you get close enough, then basically you can't get back out again. But another effect that happens close to a black hole is that everything gets redshifted, and I've just put those little dots on to indicate the redshift effect. It affects time as well as space. And these effects are well known in physics and astronomy. And here's a picture demonstrating the bending of space, bending of light. These big fuzzy objects are distant galaxies in a cluster, and these arcs we can see around are actually distant objects, the light from which has been bent by the enormous gravitational field of the cluster into separate arcs. And this arc, that arc, and several other arcs all belong to the same background galaxy. So it's acting like a gigantic lens on the background universe. Such things are quite commonly seen in astronomy now. In terms of the bending of time, or the effect on time, gravitational redshift, it's a tiny, tiny effect, but it occurs on the surface of the Earth. As you go away from the Earth, so you don't notice it, but somebody looking at my watch from out in space will observe it to be running slightly slower than if my watch is next to them. And that's because they're looking down in the gravitational field, and it will appear to be running slower. This effect is absolutely tiny, but it's crucial to sat-nav and GPS. So your sat-nav includes general relativistic gravitational redshift, because if it didn't, you would end up with an error of 45 millionths of a second per day. 45 millionths of a second sounds like something very tiny, but if you're driving around, it corresponds to 10-kilometer error per day. So if you went on a drive for 2 hours, you could end up a kilometer away from where you thought you were. And that's due to relativity, this gravitational redshift effect, which has to be included. Anyway, I want to talk about astrophysical black holes. These are objects which have only mass and spin. They're where matter has collapsed down. We think that they start off where a massive star has reached the end of its life. It's got no nuclear fuel left. The core of it will collapse inward and can then collapse into a black hole. And then after that, it can start to accumulate more matter on top. The size of the event horizon, which is the waterfall I showed you, is 3 kilometers per solar mass. So if we want to find a black hole, we need to find a large mass in a small radius. You've got to find Earth mass in 1 centimeter, squash the Earth down until it's this big, it'll be a black hole. Sun's mass within 3 kilometers, or 1 billion times the mass of the Sun within the orbit of Uranus. All of these sound astronomically large or small numbers to you. Or we can have a large luminosity varying rapidly. 1 million solar luminosities, that's 1 million times the power of the Sun, varying in a few milliseconds. 1 billion times that in a few minutes. Or 1 trillion, 1 million times the power of the Sun, varying in a few days. I've already talked about that one. Okay? All of these things are seen in the universe, apart from the planetary mass black holes. We don't think they exist in the universe. Okay, the clearest evidence we have for a black hole comes from looking at the center of our galaxy. This is the Milky Way. We live in the Milky Way galaxy, looking towards the center of our galaxy. At the moment, we're orbiting the Sun at 30 kilometers per second. The Sun is orbiting the center of the galaxy at 230 kilometers per second. And most of the stars in our galaxy are doing much the same, orbiting at 230 kilometers per second. But other astronomers have looked at the center of the galaxy, at what the stars in the center are doing, and they've done that by making use of special techniques. They need to take out the blurring of the Earth's atmosphere. So they use laser beams. They don't shine the laser beam all the way to the galactic center, because it would take it 25,000 years to get there. Instead of which, they shine it into the Earth's upper atmosphere and make an artificial star there. It causes a fluorescence effect in sodium in the upper atmosphere. And then they're able to take images of the stars in the center of the galaxy, and with the artificial star there, which they know is point-like, they can then tune the telescope, they can get rid of the wiggling due to the Earth's atmosphere and sharpen everything up. And that has been done over the last 25 years, and the stars in the center have been seen to move around rapidly. This star here, S2, is going round in 15 years. It goes around this point. Okay, this is just a representational movie. There is nothing seen there other than a very strange radio source. But the star, when it's close, is going at 1,000 kilometers per second. This one is going at 3,000 kilometers per second there. Something is pulling those stars around, and that's something we believe to be a black hole. There's a black hole at the center of our galaxy, and its mass is around 4 million solar masses. When we look at a star field like this, we see many galaxies. And what we see is that those galaxies, each at the center of them, have a massive black hole. This galaxy just here, called M87, has got a 6 billion solar mass black hole. We can tell that not by seeing individual stars moving around it, but we see the effect it has on all of the stars around it. So we're looking at a group effect there. And so we now realize that every black hole, rather than just be a big ball of stars, is a big ball of stars with at the center of it a black hole. That was realized as being common about 20 years ago. And then over the last 20 years, people have been measuring parameters about this. This is just a diagram relating things. This is the mass of the black hole plotted versus the mass of the galaxy. For those of you who know about things, this is a log-log plot, and this is a factor of 10 to the 4 up here. And for astronomy, this is a pretty good correlation, okay? And these are sort of, the fuzzy things are indicating error bars and so forth. But this is a pretty good correlation. So the bigger the galaxy, the more massive the galaxy, the more massive the black hole, and there's this correlation between the two such that the mass of the black hole is about 1/500th of the mass of the galaxy. So now returning to 3C273, which has a several billion solar mass black hole at the center, we believe, I want to return to these black holes which are bright. The ones in that previous image were faint. The one at the center of our galaxy is thankfully faint, inactive. What they can do is matter can fall into the black hole, and as it does so, it falls faster and faster and swirls around, and collisions make the gas get very hot and thereby release enormous amounts of power and luminosity. That's why that is very bright, is because matter is falling into it at a rate of several solar masses, several times the mass of the sun per year. So it's growing in size as we know. If we just look at the sky with an X-ray telescope, and a lot of what I do involves X-ray telescopes, we look at X-rays that come from space, from the cosmos. X-rays have got 1,000 times more energy than visible light photons, so we're looking at hotter things. Then the sky, rather than appearing full of stars, appears full of these objects, which are distant black holes. In this image here, all of the things, apart from the fuzzy ones, which I'm pointing out, are actually black holes which are growing by matter falling into them. Come on. A little interlude for a minute is when I was a student 40-something years ago, a graduate student, not at Darwin, I was involved in rocket X-ray astronomy, and this was my rocket going up from Woomera. This is about a 30-foot long rocket here with a boost motor on the end, and it was a way of getting above the Earth's atmosphere. X-rays are absorbed by the Earth's atmosphere, so to do X-ray astronomy, you need to be above the atmosphere, and the experiment was at the top there. The next day, I had to go up range in a helicopter to pick up the radioactive source in it, and we found the motor. It's okay, the detector is actually under the nose cone here, which separated from the main motor. The motors don't often come in like a dart, but it was quite fun to see that. My experiment with a radioactive source and everything is here. Okay, the parachute didn't work. That's my detector. And that's me with the helicopter in the background on the Australian desert. Anyway, I was looking at the background of X-rays, and so I was trying to resolve this background of X-rays into individual sources, or at least get a limit on how many sources there were. Martin Rees, just before I started my PhD, had predicted there will be 7 of them per square degree. And if I go back here, he's completely wrong. There are many thousands of them per square degree. And I produced a limit on it, which was published in Nature, which is fun. Anyway, I now want to get on to one of the most recent aspects about black holes in the universe, one of the most surprising, and that is the black hole at the center of every galaxy is not just an ornament at the center of the galaxy, it controls the galaxy. How it does that is because of the enormous amount of power that they release. A little bit of equations now. Everybody here has heard of the equation E equals mc squared. I'm sure you've all heard of that, okay? I'm not asking you to derive it or anything, but it just means you can get energy from mass. When you do it for chemical reactions like petrol, which is one of the most energy efficient substances we know about, then E equals, there's a factor in front of it, which is almost 1 over a million million, or a trillion. So it's actually very inefficient. Nuclear fusion, hydrogen to helium nuclear fusion, is 0.5%. Accretion onto a black hole, dropping matter into a black hole, is 10% efficient in terms of matter to energy. This means going from there to there, you gain a factor of 2 billion. That means if you could power your car from black hole accretion, a little small black hole in your tank, you could make your fuel take you 1 billion times further, okay? But I have no idea how we could possibly make use of this. I am not going to even go there. But what this means in terms of black holes in galaxies, the black hole, even though it's 1/500th of the mass of the galaxy, in growing the black hole, the amount of energy it releases is more than 100 times the gravitational binding energy of the galaxy. When you grow the black hole at the center, it's releasing so much energy, it could just blow the galaxy apart. It doesn't blow the galaxy apart because it can't couple to the individual stars. But what it can do is it can blow the gas of the galaxy out. And we now think that that correlation between the mass of the black hole and the mass of the stars is due to the fact that the black hole grows until its mass is sufficient to blow the gas out of the host galaxy and switches the galaxy off, and it blows its own fuel away, so it switches the galaxy off and the black hole off in terms of accreting. And so you're left with the two things related. Now this means that this thing at the center of the galaxy, which has got a size actually, its mass is 1/500th, but because it's a black hole, it's tiny. The ratio of the size of the black hole to the size of a typical galaxy is the same as the ratio of the size of an orange to the size of the Earth. So imagine something the size, the mass ratio like that controlling the Earth. That's just giving you some idea about the impact that black holes may have. And this is just an artist's representation of a black hole doing that, blasting everything away. So that means that many of these galaxies are red and dead rather than blue and forming stars. These galaxies like this with disks, like our own galaxy, is spiral arms, it can't blow that away, but it does actually blow it away in these big so-called elliptical, the big blobby galaxies. Also, what we've been doing is finding dramatic evidence of that, how the black hole can control the surroundings by looking at clusters of galaxies. These are individual galaxies in a cluster called the Perseus cluster because it's in that constellation. And this galaxy in particular is my favorite galaxy. And we're now going to an X-ray image of the same space This is an X-ray image I and my team made a few years ago with a few weeks of data from this satellite. And what we see is dramatic evidence of the way in which the black hole at the center, which is there, is actually pushing the gas away and changing the whole shape and structure of that gas around that galaxy. So we can actually see the effect of the black hole by actually imaging in X-rays what is going on. And what we've seen as well, looking away from it, we can see ripples in the surrounding gas, and those ripples, I think, are sound waves. They're pressure waves, sound waves, and they represent the deepest sound note in the universe. And so I am in the Guinness Book of Records for having discovered the deepest note in the universe. For those of you who are musical, it's around 54 octaves below middle C. Nowadays, what we're doing also is understanding how these things called quasars work. And what we find is that most of the energy that comes out of them is released very close to the black hole. And I want to take you a little bit in the last few minutes over what we're doing at the moment with this. The material swirling into the black hole is doing so very rapidly. It reaches half the speed of light at the innermost radius. This is a computer simulation of the material. We can't actually directly see this swirling material at the moment. And this side is brighter than that side because this is the approaching side. And because we've got this swirling material, it basically is magnetized and actually energizes lots of loops and filaments of magnetic field which give off a lot of power, rather like the sun. This is the surface of the sun, and there's an image of the X-ray image of the rotating sun. And the area above the sun is known as the corona. We actually think of the accreting material because it swirls in. It swirls in this disk. It's a slice through it. This is the black hole. And above it is this corona, which is powered by magnetic fields from the disk. And we see this directly, but also we see this irradiates the infalling material and produces what we call is reflection of the disk itself. So what we're doing is X-rays come from this source, and they're accreting they're illuminating the accretion flow, and they give rise to spectral properties, spectral lines, which we can see. This is a slightly technical slide, but I just want to indicate that we are measuring things close to black holes. And the blue line, which was made by my student a couple of weeks ago, is what we expect the emission to be that's coming from the infalling material. And the red line is how we observe it. And those are data points from a satellite called NewStar, which we've got. And what we see is how this emission has been blurred to the left because of we're looking at material which is very close to the black hole. It's swirling into the black hole, and we're seeing this red shifting effect on the spectrum, which is spreading the light towards the red part of the spectrum. Okay? So the data look like that, and they look completely blurred because they're produced very close to the black hole. I'm showing this as a way, it's got data points, error bars, and so forth in. This was made just a few weeks ago, and it's an indication that we can actually see effects and measurable effects from extremely close to the black hole. Another thing to corroborate that is we also would expect that if this varies, that variation will come to us directly. We can see that directly, but also it comes off in the reflection spectrum, and we'd expect to see the reflected spectrum delayed by the different time it takes. It will be an echo effect or reverberation, if you get the idea. So this changes, we see it straight away, and we see it delayed because it's gone off there. Okay? So it's just an echo effect. Now, I say we see it straight away. The kind of objects we're looking at are like 100 million light years away. So it takes the light 100 million years to get here, but we're looking for variations of just a few minutes. And this is one of these spectra, again, produced this year of time lags between the direct and the reflected paths. And you can see the timescales are a few minutes. And we can see, again, this characteristic spectrum, which this is due to iron in the infalling material. What about the future? For the galactic center, we can start, radio astronomers maybe can start to produce images. Maybe with M87 we can do images. And in X-rays, we're looking forward to new telescopes. Just a simple indication of this. One exciting experiment that astronomers are looking at is so-called Event Horizon Telescope. This is a telescope with which they hope to see the event horizon, see the shadow of the black hole at the center of our galaxy. And it will involve telescopes in Hawaii, in California, in Spain and France, in Mexico, in Chile. And what they do is they operate these telescopes in the millimeter band, so they're essentially detecting microwaves from these distant objects, from the center of our galaxy. And there's an enormous data rate because what they're going to do is record everything and then combine it all together as though this is one giant telescope. It's the biggest size telescope you can make on Earth with a diameter of, you can see, 9,000 kilometers. And they hope to get an image like this. And that image will look like this. This is the material falling into the black hole at the center of our galaxy. This is the approaching side. That's why it's brighter, receding side. And that will be the shadow of the event horizon. So hopefully in the next 5 years, they will be able to achieve this. And hopefully the actual situation here will be simple enough. I think they are somewhat optimistic in order to see this wonderful picture. I myself am looking forward to more images, more telescopes. So this is a telescope called Astro H, a Japanese US telescope that I'm involved in, which should be launched at the end of next year. And then, this is my last slide, only last month we heard that the proposal we've made to the European Space Agency for a new generation X-ray observatory was adopted. And this telescope is going to be cost €1 billion and hopefully will launch in 2028. So maybe in the 25th anniversary, somebody else will come here and tell you about the wonderful discoveries from that. Otherwise, black holes are just part of modern astronomy. They're exotic objects, but they also have important influences on the lives of galaxies. Thank you for your attention.